Looks like I'm gonna have to change my sensitivity a little bit. Your sometime. Let's see if anybody else is still interested. No pets allowed in this classroom. All right, let me boot up my screen. Seven people, only 3 slots left. If any of you are actually using CE and Monster Hunter World, you can keep following up if you want.
Are you inviting us to spam you with DMs all day?
No, I mean just in the classroom channel, the voice and the text channel, you can just, if you have any questions or issues of finding something, you can let me know.
That's not as fun as DMing you, though.
Yeah, but if you DM, it'll pop up on the screen.
Thinking.
Thinking. All right, we got 7 people watching. I think I can go ahead and start it. If you are going to keep up, you're going to need this. This is to allow the debugging for Monster Hunter World, unfortunately. You usually don't need it for any other kind of game, though. Just happens to be this crapcom. Okay, first thing we want to make sure is if you're debugging, make sure you're on hardware breakpoints under settings of Cheat Engine. You have the debugger method on VEH, because that's what we're going to have to use, and you have to have the bypass for it, and everything else should still be default. So if you have that, just okay. Yeah, this is the first entry on my table, so if you have my table, you don't have to copy it, but it would be a good idea to just wipe the table and just have this, because you want to learn how to get to pointers and debugging. Let's go ahead and go in-game. I'm going to use my character. And we're going to start with something that's simple, since every video game has it, health. Now, it depends on every game, but health can be an integer, or it can be a float, or in really worst cases, when programmers really get stupid, they can make it a double.
Have you ever played a game where it's a string?
No, I've never seen one in a string, but I'd imagine maybe the old games could do that. But then again, your health is going to appear as a bar in most cases, because early days we didn't have numbers. We just knew there was a bar there, and that was it. Okay, so we know our health is 150, but when you pull up your Monster Hunter panel, all you see is an integer here. That's a display value. It's not going to be any good to you. What we do know is that it's 150 in a float. So the best way to go approach and find that value is we'll head into an expedition. Since we can eat the max potion, for example. And it's going to be different for everyone. So if you have a health boost, you're just going to have to pay attention for how much health you start off with. And in every video game, if you take damage, that's another way to change the amount of health you have. So you can either scan for an increased value or decreased value. If you come across a game, unlike Monster Hunter World, where it's kind of obvious, but you only have a bar and you don't have a display value, it doesn't tell you if it's 100, 1,000, because let's say Dragon Ball Z games are 50,000 HP. Shooter games is always going to be 0 and 100. That can get really difficult to find. So if there's any other indication to finding something like that, it's most likely going through your profiles on your characters. That'll show you how much you actually have. But in Monster Hunter case, we're going to search for my value, which is going to be 150 in float. And since I haven't taken any damage, we know its precise float is 150. You can add a bunch of zeros after the decimal point in this case, so that we can get rid of all the truncated values that we're not interested in. And we're going to go ahead and search that. You should get probably around, I get 14,000, you'll probably get around the same amount. If you remove that zero and just search 150, you're going to unfortunately get a hell of a lot more. So it's always good to go for a precise value. So once you have that, you need to see if you can change the health. In my case, I'm going to eat the max potion. And my health value goes up to 200. So once again, keep the decimal points and search 200. Or if you don't have the health boost, you're going to be searching for 150 most likely. And we're going to do a next scan because we want to keep the previous results. All right, so we have 43 results. It's kind of a pain in the butt because we have absolutely no clue out of all of these which one is the true value. So there's going to be two values, true and display. Game uses displays for things like this right here, where your health is showing up as 200, stamina is showing up 100. Those are display values. They change based on the true value, which is hidden in here. So the best way to find out what we're looking for is right-clicking and find out what accesses this address. So before we do this, enable your VET because of this stupid debugger that this game has. Once you turn it on, let's click on the first result that you may or may not have. Find out what access it. Yes, I want to debug it. And we already have results. Let's have a look at it. Okay, so this one is being accessed constantly. And this is 20 offset. I know for a fact that's not it. And the best way to test if it's not it is if we change the value, see what happens to our health. Nothing. So that's a display value. Can't use that. So we're going to go ahead and try the next one. Change it. Okay. You'll notice my health did change for a matter of split second, but it went back up to 50. So this is, again, a display value. And it's most likely related to the bar's percentage of where it's at. So let's try the next one. 50. Okay, we found our health. One reason why I'm saying we did is because I got disconnected and it has a checksum, unfortunately. So when you're playing online, it's going to kick you off. We found our health, so we're going to go ahead and right click that. Find out what accesses it. And this is where the pointer stuff comes in. There's a lot of access, so shut it off as soon as you can, because you only need about 3 results. First thing we should look at, though, is the offset. You'll notice that all 4 of them are the same. Of course, the register isn't, which is okay, because that's the base address of this specific offset that we need. And we need this because we're going to repeat the same procedure we just did with the health value for that address. You're going to grab, in this case, it would be RAX. This is the base address for the first offset. You're going to copy it. You're going to go ahead and dump this because we now have the health that we're looking for. Go to a 4-byte, change it to hex, and paste that address in there. And you're going to hit first scan. In rare cases, you'll get thousands of results. Luckily, this game isn't being so retarded, and it only has 3 results. So we're going to do the same thing we did with the health. We're going to right-click it and find out what accesses it. This one has no results. That's not good. That either tells us it's a bad pointer, or the game doesn't even bother reading anything from this. We'll try the second one. Same thing, find out what accesses it. And we got a whole lot of results. So we're going to stop it. And we're going to look at this offset. Okay, this one is 7630, and they are all identical, which is good. You want to make sure these are always identical, because that means that's the true offset for a pointer that the game uses. And I know a lot of people make this mistake. What they do is right-click this value, pointer scan, throw nothing in here, and just hit OK. You're going to get billions of results. And the main reason because of that is there are 3 types of pointers: temporary pointers, static pointers, and true pointers. The temporary pointers only work for your system and only for this specific session right now. If I close this game and start it up again, those temporary pointers are useless. The static pointers will always work on your system. They're similar to the temporary ones, but the thing about it is, if you were to share that pointer with somebody else, it wouldn't work for them, because it only works for your setup, your motherboard, your hard drive, all that combination. It's just something, and it's usually tied to the CPU as well, because there's sometimes issues with AMD and Intel. That's just the architecture. So we don't want that either. What you want is the true pointer, which is a pointer that the game intentionally uses, and they always end up in the same offsets. So we have 2 offsets. Open up a notepad or something, because you're going to want to do this whenever you find something. The first one was 64, or in this case, the last one was 64. The second last one was 7630. Okay, so we got 2 offsets. That really narrows down how much pointers we're going to find. Usually with 2 of them, that's enough to find a pointer. So what we're doing is we're going to right-click, we're going to generate a pointer map for that health value. So you can just save it, whatever you like. In this case, I'll call it health PTR as health pointer, and let the game dump everything that's right now in the memory. It's going to take some time, so let it roll. So any of you managed to find your health yet, or get close to that point? Why does scanning her value on the register produce results? The game is accessing a specific address. In this case, this one's about 3,000, because when I stopped it, we ended up at 3,000. This is the most accessed one. If you were to follow it and find out from this instruction what is being accessed, you'll see Okay, there's a 50, there's 100, there's another 100, there's 150, and 100. When I did this in town, I noticed I got a hell of a lot more resources. You have to understand that the last offset is just an offset to a specific actor. So in this case, this is me. This could be that dumb guy next to me. That could be the guy currently eating a potion. They're all there. You don't want that. You want an instruction that only focuses on you. Here you have a ton of them, actually. This looks like one of the monsters, for example. 19,200, another one 17,995. In fact, if I were to set this one, for example, to 0, maybe a monster died. I killed Tigrix on accident. Whoops. So there's an address that basically accesses every actor that's alive right now. You also don't want that. So we're going to go ahead on the other one and see what that one accesses. Again, we've got a crap ton of results. We don't want that either. Try the last one. Same thing. Find out what accesses it. Okay, this one's a little better. It's only 4. We can work with that. All right, our pointer scanner is finished. So now that you have the pointer scanner finished, you can now do a true pointer scan. You want to load up that map you just got. And now remember those 2 offsets we got? You want to put those in here in that order. And if I remember correctly, that was a 7630. We're not sure what the next few pointers might be. In some cases, a game will have 4, maybe 5. We're going to go ahead and set it to 4 max offsets. And we're going to set this up to maybe 8,000, give or take. We're going to go ahead and let it scan that. Going to save it as hell1 because this is our first scan. I already did one, so I'm just going to replace it. And let's see what happens. It's going pretty quick, which means we've narrowed down the results. And you'll see the results go up quite significantly now. Okay, so there's 152,000 results. That might seem like deterring, but it's not. We're going to order this list by offsets. And we're going to see what we get from lowest. All right, so lowest we've got 3. There's a maximum of 3 offsets for the lowest possibility. That's not bad. You want to avoid these kinds of pointers. They're redundant. They're not going to work for you. You want to make sure that the executable you're dealing with is the base address all the time. The next thing you want to look for is the base address common value. In this case, we've got 750 here, we got another 750 here, we got a 418 here, and another 418 here. So you want to go through that and see how many times that pops up. If it pops out a lot more often, it means you found a good base pointer. So I chose, for example, I chose the 150 in my case. I saw that that thing was there about 5 times. And I decided to go with the lowest first offset I could find, which was this one. So let's go ahead and throw this guy in and see what this base address is being accessed to. So I'm going to take it out, throw it in its own separate thing, and hit access. If we're lucky, there should be hundreds of access points. If we're not lucky, then we probably found a dead beat. It's not going to help us. So we're going to try another one. Take this guy's address. And we're just going to replace it. See if we get anything. Okay, we got something. So that means we're close in that range. We're going to look at the assembly and see what it does. If anything familiar comes out. When you're in that assembly here for the instructions, you can scroll down and see what it slowly does. If you see any of the pointers we already scanned from our notepad, then we're on the right track. If you don't, then you're either going to have to do a break and trace on it and see if anyone pops up, which is a lengthy process. So you want to avoid that unless you're absolutely not certain that this is the right address you want to find. But in this case, I know that this is the right one. And since we already have 2 offsets we got mapped out, our results are much smaller than they would be if we just had used one, or if in a case none, which a lot of people do, is they just say right click, pointer scan, and then get billions of results. That's the bad idea. Always make sure that when you find a value, right click it, find out what accesses it, and consider this offset as your first offset scan. If you can only find one, that's okay. Just take that one, throw it into the scanner, and see how many results you get. If you can trace it further back, like here, for example, when we go to show an assembler, and you skip back 2, you'll notice that 7630 shows up here. So these 2 are important because RAX, the register RAX, is being thrown in here from RCX 7630. And that's being associated to it. Now you could do the same thing with the register RCX. Of course, the problem is it's coming from a call because there's a return here. And it's returning here after it. So what you could do is you could right-click this, break and trace, leave it at 1,000. Doesn't matter how many steps you're going to do. Wait for it to populate. Open it. And then look at what we get as a result. You'll notice that RAX is 0 at this very moment. But when you go down, it has this value. And if you look at RAX plus 64, you'll come to this value, 100 health. Of course, that's not my actor right now. This is one of the actors inside the game, probably one of the monsters, the small ones. They only have 100 health. And from here, what you do is you go to this return, and you know that the next step is where the call was. Because if you go back here, and you go into the assembly, and you skip up to, there's the call. So it ends up in this location, which is the same sequence we were looking for earlier. Of course, this instruction accesses all actors, which makes it kind of difficult to get your health from time to time, because whenever you do a break and trace, you might accidentally hit the 10,000th cycle, and that happens to be one of the small monsters. This is why I said when you're doing a access, you want to make sure you get one of them that only focuses on your player. So now that we have that pointer, we can close all this. We can go back to our pointer scan. Cancel it because we already have it. Open it up. Let's get health 1. And there's going to be some invalid values. See if I can find any here. These are crap. These are invalid. They pop up and then they disappear. Those are temporaries. They're useless. They're not going to work for us. So we're going to rescan and filter out all invalid ones. You're going to save those results as a new file name. And we went down quite significantly. So here we have, we took this one, which is, should be this one that we just selected. So we're going to get rid of that. So now you have a pointer for health. If you were to restart your game, I'm not going to do it now, but that value should, once you get in town or once you get into an expedition, be, again, your health. Now, if you share that with somebody, it should also work for them because you just found the true pointer. If this was a static pointer, it would only work for you and nobody else. So this is one way to find a pointer, a true pointer for, say, your applications that you make, like the time of day that Kerr did, I think it was. He had a long pointer, and it worked for him, but not always for everyone else. But what happens if you only have one result, one offset, and you don't know what the other ones are? Let's see which value we can do here. I'm going to take one of the items as an example. Say, let's do potion. So we're going to search for 9, since that's my current potion value. Too many results, so we got to change it. 6. Still too many. Still too many. And still too many. It's probably a good idea if we do one more change. There we go. 4. Okay, so we have 4 results. Again, one of them's the true. Everything else is a display. Let's grab these 4. And let's change the first one to 20. See if anything happens. You'll notice that all the other ones changed. So we may have found the true value. And we did. So this is the true value. Everything else is garbage. You can get rid of it. And you're going to find out what accesses it. Of course, one of them's already going through it, but that's only one result. So what I'm going to do is going to move the mouse. That should change a result, because the game has to execute a code, and decreasing it, increasing it, should also give me new results. I'm going to stop it there. So we know the offset is C. That's all we got right now for this item. Let's see if we can find out about a second offset. And this one's actually particularly more difficult. We have an instruction, and the problem is there's 2 jumps involved. We can't break in here because we have absolutely no clue if or when it goes inside here. So we want to be outside of a jump. Let's say here. I'm going to break and trace that. We're going to go back to the game and decrease it. Your game's going to freeze if you got it. We didn't get it. So we're inside a skip. There we go. It did function. It was the increment one that we were looking at. Okay, so now you have to find that particular instruction we were looking at, and that was here at DB872C8. And that should be here. And it should be the value we had before we changed it, which was 5. Right, because we're at 6 now. So now you can go up and look where that REX is coming from, because the offset REX is what we're looking for. And if you do the same thing I taught you before, grab this address and throw it in here by doing a hex scan. B28100 and search. We got 1 result. You're probably saying inside your head, yes! And I'm going to tell you, no. Let's go see what happens when we access it. Nothing's happening, because the only time it does get access is when it increases. Let's see if that happens. We get nothing. So either this pointer is being manipulated, or it's being changed somewhere else before it even gets to C. So we have to backtrack it. And backtracing is one of the more difficult things, because you can only trace forward, you can never do back. So to do that, you have to learn how to go from returns and go 1 step back so that you end up always in the same spot where you started. To do this, we need to be in the exact same level. So here's the level where we were. We need to follow this level down to its return function. Go to the next step, and the step previously from that should be the call where we were, and that's here. So we're going to break and trace from this point on, leave the other break trace open so we know where we are. Going to increase it, say to 500, and hit OK. Going to increase our item so that it triggers. Your game's going to freeze, so don't panic. We're going to expand all of them. I'm going to throw this one on another screen so I can compare it. And we're going to look for that instruction where we were, and that was DB872C. The best thing to do is to collapse, open this, and follow through from where we went to the call, which was here, because we break traced here, and the call starts all the way through here, and we're looking for DB872C. So we got a long way to go down. Should be, nope. Let's see, DB72C. It's not in here, is it? If we compare this, this is where we should be. We need to go further down, but it's not present. Only goes far to A. Why? This is the part where you worry because you don't realize the correct sequence is not here. So we found problems. So we'll go back to our access and look at it one more time. We should be here. We did a break and trace up here and got results. Let's try it one more time. Make it increase. Expand it, and we should end up here. So this means the instruction is either iterating through multiple results before it ends up going here. Alright, so we're going to go ahead and follow that call again. Go back to the return and break and trace in front of this. I'm going to increase it to 2000. Because it might be that we are going through multiple iterations. I'm going to increase it one more time. Expand. And now comes the part where we have to search through this thing. Highlight this so we know where we need to be. Collapse and get to the first call sequence. And go follow it down. Till we get to 8, 7. There's nothing. Okay, so this is the first iteration. Let's try, see if there's a second one. It's a lot of functions. And it's killing us because we're not getting to DB. We need to find DB87. Hold on, here's DB8, but this is F. We're too far in front. But here's DB8. DB8D, still too far. It's close to what we need to be, but it's not on the right. Here we're back to DB86. That's where we need to be. Keep following that down. DB86. Still in the 6s, still in the 6s. Now we're in the 7s. But we're not in the 200s. That kills us. Gotta keep going down, see if we can go further. Here we go again. Okay, here it is. We finally found it. Here's DB717, almost. A lot of calls, unfortunately. Keep going down. Let's see, DB2C. Oh, still not there. Still not there. Oh, and the call is the trace. The break and trace is too short for us. That's not good. So this is a little bit more complicated. Can't do that. So let's try a different instruction. Let's pick this one. See what this instruction gives us as a result. And I think all we have to do is hover, which causes any item, unfortunately. I did the max potion in this case, but we want to do this on the health potion. Break and trace. Move my mouse over it. Expand. Okay, here's C. And that should be 8 or 9. There it is. We follow it down once again. Best way to do this is just to open the last set. Just keep going down until you finally see that return. Wow, that's a long instruction. Here it is. Go back to the previous, before the call. Unfortunately, we need to unselect our potion first. Break and trace. See what the potion does. And expand. Now we need to find from our last break that, which is on DB8A. Oh, this is going to give us better results now. We need to go to C on the next level. Okay, C, D, F is the last sequence. Come on, we're almost there. Here. So we found it. Now we need to backtrack it. Find out when RBX becomes this value here. So I'm going to take a note of this value, this address, because this address is being used as an offset. So we need to find the pointer that leads us to this. Okay, so we're going to trace everything back. RBX is our goal. Do not take your eye off RBX. Keep tracing back until you see something like this, for example. RBX and RAX just suddenly changed. So there's something happening in here. Need to find out what. When does that value? Here it is. We're moving RCX into RAX. Oddly enough, that changes this, but it doesn't seem to change anything with RBX. So we can keep going up. Until RBX changes. Here it changes. Why? Because we're moving RAX into RBX. So now RBX is no longer our target. Now it's RAX because our address is over here. So now we're tracking what happens to RAX. So keep going up and wait till RAX changes. Uh-oh, here. Alright, so we've just found the most unusual way of offsets. And I've noticed this with Colf. Sometimes that particular offset, like we did here with RBXC, is not the true offset. Why? Because it's being manipulated over here. Our base address first is being added 38080. So we're going to take a note of this. Okay, I didn't copy that. It's shifting over. So it actually is 3808, interestingly enough. We'll make a note of that as well. And it's actually here, and it's adding to RAX, the 3808, which means what is RAX before that? Here it is. This is what RAX is before it adds something. Okay, so now we have to, didn't copy it again. I gotta type it out, unfortunately. All right, so let's scan this address because this seems to be the base address we're looking for. And there's one result. Okay. Let's see what happens. So we're gonna need a calculator. We start off with 84 AF0080. What it does next is it adds 3808 and it shifts over to another 0 and then adds it again with this value, RCX. So let's put that address in there instead. 84AF0080 plus 38080. And we come up to this address. And if I'm not mistaken, we had that address before, and we know from this address, it's plus C. So the actual total offset has to be 3808 C. Let's test it out. Grab this address, throw it in here, throw that offset in, and there it is, 9. So now we know this is the base address. Let's see if this address truly is, and it is, our access is giving us information. So its next offset is A8. So now we need to know what RCX is. RCX is close to the original. So we're going to copy that and throw this one in. Keep this open because this is your next offset you want to take note of for that specific item. So I'm going to throw this right under this offset. I'm going to put that new address from RCX in here and scan it. Okay. Whenever you see a green address like this, that means you found a base pointer. And if you double click it, it'll automatically fill out with Monster Hunter World. So this is our base address. We know that for a fact. You notice this one's a dummy here because it's constantly switching around. And the other ones feel a little bit unusual, so we're not even going to bother touching them because we already have a green one. I'm going to copy this address, pointer, add the base address. You'll notice we get that address we had before, and we know the game adds 8A because that was the first offset we were looking at. I'm going to go ahead and add another offset. You'll notice the address we got after that is 84AF0080. And we remember that it was doing this weird 38,000 calculation, adding it to that address. So we're going to throw that in, plus the C, which is the end address that was being used by the pointer. So it's going to be 38080, but there was a C involved. And when you look at that, you have the base pointer for your health potion. Let's see if it's true. Yep, seems to match perfectly. Seems to change. Now, different pointers are going to lead you to different results. In this case, we can't say that this pointer is going to work for our second character. For all we know, this pointer may only work for this specific character right now. If we were to switch to our second slot, this thing will not update. And that's one of the things you have to find out in the instructions if there's another calculation. The only way we're going to be able to figure that out, however, is if we go to our second character and see what kind of result we get with that. If I had to guess, and that's only if I had to guess, it could be the save region. But we're not going to go that far. So now you know that getting the proper offset through what accesses something are the pointers you need. If you do a scan just like this, and you say, let's see, how large was it? 2 pointers. And the last one, unfortunately, is huge. If you do a pointer scan for this, you don't even bother changing this, and you know it's 2, and you don't know the offsets, and you didn't save a pointer map, and you do a scan like this, you are going to get a really slow process, and eventually a lot of results. But let's see what it does in the meantime. All right, so I'm going to hop off just for a second. I want you guys to, if you have your time, pick any value in the game, whether it's an item or a health bar or some other value you can see. I want you to grab it and find a valid pointer for it through the process that I just showed you by using what accesses this address. Write down the offset and repeat this process until you can't find one. Do a pointer map, and then cross-reference that pointer map with the offsets you actually have, and see if you get any decent, true pointers. In the meantime, I'm going to look and see what kind of questions there are. Yeah, everything will eventually reach a base pointer, but it will not always be a true base pointer unless you use this method. And even if you only get one offset and you're absolutely incapable of finding the next level, it should still give you enough results. The alternative to that solution is that you have to restart the game probably 2-3 times to see how many of the pointers that you've collected are valid. Meanwhile, I think my pointer scan should be, in this case, my pointer scanner is done, and it had absolutely 0 results. And the reason being is, this is 38,000, and the value I was scanning at maximum was only about 8,000. So the actual offset would have been no more than 1F, 9F. So I would never have gotten to the, and what was it? About 38,000. Let's see what the offset of 38 is in an integer. It's actually 229,000. So if I set the pointer scan to 229,000, I may get results. Let's try that. This is the dumbest way of finding pointers, by the way, but I'm just going to show you what normally typical people do without doing the whole find out what accesses it and without using a pointer map. Oh, right. I'm supposed to put an integer here, not the hex value. And we're going to go a little bit higher so we don't miss anything. All right, let it scan again. This is basically the lazy method of doing things. If I had to guess, there's going to be at least hundreds of results, if not thousands. Now, since we have the health value in here, let's go ahead and return to town. Another way to determine if a pointer is bad or good is to make changes in the game happen. My health value should change, and it shouldn't change on address, most likely. But we're going to observe it and see what happens. Now, unfortunately, I'm multitasking, and it may confuse you because I'm doing a pointer scan, and at the same time, we're looking at the health. And you'll notice it just did. The address is still the same, but the health value is 150, because that's my base pointer. Now, this is a player pointer. Another thing about interesting pointers is this is the region of your actor. Oh, looks like our results came in. We'll take a look at those later. That means that 64, our health, is here. Let's have a look at this memory region. If you scan through these 4 bytes and see if there's anything else in here, you may come across some peculiar values that could help you. Like here we have a 0.08. That could be anything from certain speeds of movement to other notable character data. But you can find, in this case, back here, you'll notice there's 150 here, and there's 150 here. I know that this is my health, so if I change this to 88, this changes. But what happens if I change this? Nothing. It goes back. This is the display value that we were talking about way earlier. That's not our valid pointer. Okay, this is 1. This is 1. This is 1. This is negative 54. Seems like a valid float. Another negative 04 seems to be a valid float. 0.36. Let's see what we got here. That's the health. So this is the health region. The other way you could do this is you could just up the value until you come across something that you may think looks familiar, because it's related to your character. No, that's not what it is. Ah, There's 100 here. Okay, we found something. Hang on. So when you iterate through your actor pointer, we got 100 and 100 here. Let's see what 100 here is. That's 3C. One. See? Okay, so let's see if there's anything that looks familiar here. We're most likely at our stamina. And we can find out real quick if that's true. Let's set it to 120. Nope. So this is the display value. See if the next one is the true value. 120. Changed again. This looks like another display value. There's a third one though. Change that to 120. Something changed. And you'll notice the display values changed as well, because now we have 120 stamina. So the structure of your character stores health, stamina, possibly position, character animation status, things like that. And this is how you start getting, because somebody asked, can I find out what animations bleed into other animations? And you're probably going to find that here as well, because it pertains to your actor or your character. So if I try to change this to 200, which probably won't be possible, it goes to 200. That's the max. So you can go from a pointer to a completely new thing. When I first started, I wanted to find out how I can uncap stamina. That was my next step. And this is where you combine the pointer concept and the instruction axis. For example, let's change it to 300. Nothing really happens. So there's nothing new showing up that tells me how much the max really is. I'm going to stop it because otherwise we're going to overload here. But when I proceeded to do this, I came across my other information in my table. Eventually it grew, and I found where the PL params are. And the people who work with mods already know what I'm talking about. It's the PL params is the player parameters that are being loaded up when the game starts that informs you about your initial data. And that's how I ended up getting to it eventually, is I was scanning the health and the stamina, changing it around, breaking and tracing, and finding out what writes to this address. Instead of access, because the game will consistently access something, if you want to find something more specific, like what writes to it, then this is where you want to go. So when you take that ancient potion, for example, and your stamina boosts up to 150, this is going to help you a lot, because it'll tell you what instruction now writes towards that address, and from there you break and trace backwards. And again, remember, you can't break and trace backwards. You can only break and trace forwards, but you can follow the steps to a return and then step 2 back to the call that causes you to enter that state. And that's what I did in order to obtain that information. And in turn, you could also find information about your character movement, how fast your character tilts to the left and right. And that was all part of the PL params, for example. All right, so looking at the pointer we just scanned, which was our potion, you'll notice we finally got results. And they're pretty huge. But luckily there's only 775 results. I'm going to sort them in order from decreasing. And we notice this was the one we found. But you notice something familiar? All of them end in C. Every single one of them. This tells you you found the right pointer, because the instruction always ends in C. But if you had done just C, you would get no results. We did not know that there was a manipulation happening with 3808. And because we did that trace, we found it. And that's going to happen a lot with some of the pointers. Another thing that's important about is the base address. You'll notice the smallest base addresses are very important, and they linger with others. So you'll find out that your health, for example, was 04C E4150. If we go back to our